Good afternoon and welcome to today's webinar on beneficial coal ash reuse, impacts and barriers to entry. My name is Catherine Klein and I'm a technical advisor at NARUC Center for Partnerships and Innovation, where I support DOE NARUC Coal Modernization and Carbon Management Partnership. I'd like to begin today's webinar by introducing our moderator, Deputy Chair Chris Petrie from the Wyoming Public Service Commission. Governor Gordon appointed Deputy Chair Petrie to the Public Service Commission effective February 1st, 2021. Prior to his appointment, Commissioner Petrie served as Secretary and Chief Legal Counsel for the PSC since 2007. In that position, he provided legal advice to commissioners and presided over as a hearing officer and case manager over significant contested case proceedings. Commissioner Petrie received a BA from the University of Wyoming in Political Economy and a JD from the University of Wyoming College of Law. Commissioner Petrie is an active member at NARUC, and he's currently serving on the subcommittee on clean coal and carbon management. With that, I will pass things over to Commissioner Petrie. Thank you so much.
Thank you, Catherine. And thank you for joining the NARUC Subcommittee on Clean Coal and Carbon Management for today's webinar on beneficial coal ash reuse, impacts, and barriers to entry. Please note this is the second part of a two-part series. If you missed part one, you can view the recorded version on the NARUC YouTube channel. This webinar is possible due to support from the U.S. Department of Energy, NARUC Coal Modernization and Carbon Management Partnership. We thank the DOE Office of Fossil Energy and Carbon Management for supporting NARUC's technical assistance activities for state regulators on coal and carbon management topics. A couple of housekeeping notes. This webinar is being recorded and the recording and slides will be posted on NARUC's website and emailed to attendees next week. Please enter questions into the Q&A box and we will get through as many as possible following the presentations. Now I'd like to introduce our webinar panelists, beginning with Thomas Adams. Thomas Adams has been the Executive Director of the American Coal Ash Association since February 2009. Mr. Adams has over 30 years of experience in the ready-mixed concrete industry in a variety of management positions. Mr. Adams is a fellow of the American Concrete Institute and a recipient of the National Ready-Mixed Concrete Association's Richard D. Gaynor Award. He is a native of Detroit and attended Wayne State University and Aquinas College, studying business administration and strategic management. Tom Sarkis is a senior managerial and technical advisor at the U.S. Department of Energy's National Energy Technology Laboratory, where he has over 36 years of technical and managerial experience, including 30 years in project management. Tom has hosted over 20 technical conferences on topics of unburned carbon in fly ash, SO3, reburning technology, selective catalytic and non-catalytic reduction technologies for NOx control. His specialties include clean coal technologies, air pollution control technologies, flue gas cleanup, advanced coal-based electric power generation technologies, and carbon capture and sequestration. Kara Fornstrom is the director of the Center for Energy Regulation and Policy Analysis at the School of Energy Resources at the University of Wyoming. Prior to joining SER in December 2022, she was the director of state regulatory policy at the Southwest Power Pool, where she focused her efforts on expanding electricity markets in the Western Interconnection. Previously, Kara served on the Wyoming Public Service Commission for 8 years. She received her bachelor's degree from the University of Wyoming and her Juris Doctorate from the University of Nebraska-Lincoln College of Law. And so we'll begin with Thomas Adams and his presentation.
Thank you very much. It's a pleasure to be here, and I wanted to thank you for the opportunity to talk about beneficial use here for a few minutes and kind of give you a portrait of where beneficial use is right now as we are meeting today. Next slide, please. ACAA has been pursuing its mission since its founding in 1968 as a National Ash Association. Our mission is to encourage beneficial use in ways that are environmentally responsible, number one, technically sound, commercially competitive, and supportive of a sustainable global community. Those are the four criterion that we apply to a beneficial use proposal when it comes to us. So it starts with environmentally responsible and protective of human health and the environment. Next slide, please. When we look at today's market realities, I'll give you a few highlights here. In its 2015 CCR rule, the EPA said beneficial use was exempt from regulation, but it has continued to try and regulate certain uses EPA described as unencapsulated, a term that only EPA uses. The rest of the regulators in other countries use bound and unbound. Some of these uses, such as structural fill, have declined sharply as a result of this effort to regulate something that is outside of regulation. As coal-fueled units have retired across the U.S., supply of CCPs is not meeting market demand for some uses, especially for coal ash used in cement and concrete applications and FGD gypsum for panel products, also known as wallboard. We do have some good news, though, that harvesting, a term that you may or may not have heard of, harvesting of CCP from surface impoundments and landfills is helping to fill the gap between supply and demand in those markets where those harvesting activities are occurring. Next slide, please. In terms of production and use data history, we have been doing a production and use survey since 1968. We do it annually. Looking back to the year 2000, EPA made a final determination in that year under President Clinton and EPA Administrator Carol Browner that coal ash did not warrant regulation under Subtitle C for hazardous waste of the Resource Conservation and Recovery Act. In that year, our data showed the beneficial use rate was 29.5%. Fast forward a little bit to 2002, EPA joined with other federal agencies and industry to form the Coal Combustion Products Partnership, also known as C2P2. Its purpose was to encourage beneficial use. This was a key element in increasing beneficial use from 29.7% in 2000 to 44.5% in 2008, almost a 50% increase in the beneficial use rate. The actual tonnage actually doubled during that time period when you look at the coal consumed and coal burned factors. In 2009, new rulemaking started, and use of coal ash for beneficial uses stalled in place as the rulemaking process went forward. Following the promulgation of the 2015 rule, growth in beneficial use resumed. In the most recent survey for which we have data for 2022, coal combustion products use was reported at 62.25%. Next slide, please. Coal ash for use in concrete and FGD gypsum for use in wallboard is in greatest demand. Coal ash, which includes both fly ash and bottom ash, is the most widely available of all supplementary cementitious materials for use in concrete mixtures in the U.S. According to our data in the 2022 survey, we had about 36 million tons of coal ash produced, with 11.5 million tons being consumed in concrete mixtures. Market demand conservatively is estimated to be in the range of 25 to 30 million tons per year. Now, these are national figures. You have to bear in mind that we're really a network of regional markets. So some markets are in short supply, others are in good shape. But nationally, these are the numbers that we're showing. FGD gypsum is reported to be used for producing about 50% of the panel products sold in the United States market. Demand for these materials is estimated to be much higher at 65 to 70%. Harvesting activities are beginning to close these gaps. Next slide, please. If you don't know what harvesting is the recovery and processing of materials from surface impoundments and landfills for beneficial use. Now, oftentimes we get asked, well, how does this work? What are the costs for it and these kinds of things? The type and amount of processing needed is dependent on the CCPs available, the condition of that material in the landfill or impoundment, and the market is intended to serve. For example, processing for use in concrete mixtures will take more processing than harvesting coal ash for use as raw feed material for the production of Portland cement. Therefore, the cost for harvesting is going to vary at each location. We do have two very good documents to help people get started with harvesting activities. The first is ASTM E3183, which is really aimed at more at regulators than any other group. It's a standard guide for harvesting coal combustion products stored in active and inactive storage areas for beneficial use. It basically gives you a checklist to go through as you're considering allowing a harvesting activity in a particular area. The next document that came along looked at the materials. E3355, Standard Guide for Characterization of Coal Combustion Products in Storage Areas for Beneficial Use, gives another checklist for looking at these materials and trying to figure out just exactly what you have and how you're going to go about harvesting if you decide to go forward. Next slide, please. Some of the processes that you see in harvesting activities include the following. This is not a comprehensive, all-inclusive list. It just gives you an idea of what you might be looking at, bearing in mind that each time you pick up the coal ash and do something with it, it has a cost attached to that. Certainly there's excavation, there's a lot of dewatering, there's screening, stockpiling, there's blending from those stockpiles, there's a lot of drying that needs to go on, treatment may be needed to reduce unburned carbon, and storage. All of these things and more add to the cost of getting involved in harvesting. So it's capital intensive. Next slide, please. Harvesting, as I mentioned, takes a big commitment of time and money. Remember these factors. The investment for startup and maintenance is significant. Most landfills and surface impoundments have large quantities of material stored in them, and these inventories have been accumulated over many years and in most cases decades. The markets for harvesting these harvested materials can only take so much material at a time. Therefore, it will take a long time, perhaps as much as 15 to 20 years to clean out a facility. Regulatory deadlines need to recognize these facts, and when EPA was considering the 2015 rule, and when it was at the Office of Management and Budget, we pointed this out to them, and apparently when the final rule came out, they chose to disregard that conversation. Next slide today. Okay, in today's market, we look at the numbers we have for 2022. For that year, we're reporting that harvesting of coal ash for use in concrete mixtures added about 1.8 million tons of supply to the market. Very significant addition, a little bit over 10%. For 2023, we're just starting to collect data now. From what we see so far, the number is expected to increase to 3 million tons for use in concrete products. And in 2024, another 1 million tons of harvested coal ash will be added to bring the harvested coal ash being used in concrete mixtures to 4 million tons. These are the announced projects, the ones that are underway and the ones that are about to get underway. There are a number of projects that are on the drawing boards across the country at this point in time. So harvesting is a real thing for the marketplace. It's producing significant quantities of good quality material because this material is processed and available on a continuing basis. One of the problems in the market today is that power plants that are not running on baseload status are up and down, and therefore the supply of ash from those facilities is up and down. When we have these harvesting activities going on, we can produce the material at a more steady rate, which is a big advantage to concrete producers, giving them more confidence that they're going to have the material that they need when they need it. Next slide. That concludes my brief comments, and I'll be happy to answer any questions when we get to the question and answer period. Thank you.
Very good. Thank you, Mr. Adams. Now I had understood that we were going to proceed with Tom Sarkis. Have I got that wrong?
Nope, that's correct. Go ahead, Tom.
Good afternoon. I don't have any slides to use. I'm just going to talk extemporaneously today. We had a practice session and the other panelists asked me to repeat some of the remarks I made during the practice session. You know, in the US, we have an abundance of land. So historically, we've landfilled or stored a number of materials ranging from municipal solid waste to coal ash. It's not like that everywhere in the world, and I would contrast the situation with Western Europe and the countries of East Asia, most prominently Japan. In Japan, land is not nearly as abundant. In fact, if you have a power plant of any type, one of the larger cost portions of your power plant is going to go to the acquisition of land. I attribute this use of ash to a couple of things that are different economically. One is, when you look at the US, not only do we have an abundance of land, we have an abundance of a variety of natural resources, including fossil fuels, such as coal, oil, and natural gas. When you go offshore and look at the prices that are paid for these fuels in Western Europe and Japan, they're much higher. So their fuel costs are much higher, and they're sensitive to that, and they emphasize power plant efficiency to a higher degree than we do. I've already mentioned the abundance of land in the US and not so abundant in Western Europe, and markedly less abundant in Japan. So what they've done is they've developed a mindset where they essentially, well, in Japan, for example, they essentially reuse all of their coal combustion byproducts, nearly 100%. I found a couple of references online that they've shipped a few barges over to South Korea, but essentially they reuse all of their coal combustion byproducts, including fly ash. They simply don't have the land to stack wastes. So they've done things like modify the building codes in Tokyo to encourage the use of ash materials in building and construction. Another thing that I saw on one of my visits to Japan is that some of the plants where they do pond, and recognizing that thermal power plants need a source of cooling water, and in Japan that means siting the plants along the coast. So they will pond their ash out into the sea, and then when the impoundment is full, they will cover it, pave over it, turn it into a parking lot, or put some other part of their facility on that, and they've essentially reclaimed a few acres of precious land by doing that. In Western Europe, things are not quite so acute, but they do use a higher percentage of their coal ash than we do in the US. Again, we have wide open spaces, lots of land, and the land is relatively cheap compared to some parts of the world, such as the ones that I'm mentioning. Thomas Adams has already gone through. You can do a lot of things with ash. Some of them are high volume and I would say very valuable applications, such as in cement. The use of fly ash takes what would otherwise be a cement with a lifetime of 20 or 30 years, and it improves the life of that cement to 70 to 80 years. There are also even very high-tech but smaller volume applications for fly ash, things like cenospheres, that one of the popular quotes on that is that cenospheres were used in the coatings for the space shuttle because they could help the shuttle to withstand re-entry into the Earth's atmosphere. But the economics are, as I tried to say a few minutes ago, they're different around the world, and you have to look at that differently. I was first introduced to the topic of coal combustion byproducts when the Department of Energy funded 3 flue gas desulfurization scrubbers in the 1990s. And 2 of the 3 produced gypsum that was subsequently used in wallboard. And the 3rd was a smaller unit, and while it produced approximately the same quality of gypsum that could be used in wallboard, they simply stacked and stored the gypsum on site. After that, my second introduction to the world of coal combustion byproducts came after we had funded a number of low NOx burner installations on coal-fired power plants. A very successful technology, good at removing NOx emissions. And today, low NOx burners are installed on the majority of coal-fired power plants in the United States and indeed around the world. However, we started in our discussions, we started noticing that our industry participants had observed an increase in the level of unburned carbon that was present in that fly ash. And we went around to our other projects and said, have you observed something like that? And they all had, but nobody was really talking about it. So we started a series of conferences. I think we started with 60 people and grew it to a few hundred people. And we ran that series of conferences for 10 years. There are things that you can do to try to minimize the level of unburned carbon that goes into the fly ash as a result of low NOx burners and associated technologies. You can remove the carbon and try to recycle or burn it again in the boiler, because that unburned carbon if it's high enough, it could make the fly ash unmarketable. And that's not good for the power plant economics. They really would like to, 1, avoid landfilling the fly ash, and 2, if possible, to produce a small revenue stream to help offset the cost. So this is an interesting field. It's important. It's interesting that Tom mentioned that that some areas are experiencing, shall we say, supply challenges from time to time, because we have a lot of fly ash in this country. Historically, it's been produced, as Thomas said, for decades in many areas, and the piles of ash can be really large. And we also have sort of a corollary material in coal mining wastes that can be produced and stored across the country. And to the extent that we can reclaim or reuse these things, it's a very good idea to do that. Sometimes the owners, however, are concerned about potential liability in terms of mining these ash deposits. And I dare say that if there are any latent liabilities that we don't know about, I would think the owners of the ash are very concerned about that as well. So what we see is that some of the owners will allow the mining or reclaiming of their existing coal ash ponds, and others will not. They simply prefer to manage and monitor those properties. So those are my remarks today. Thank you for listening.
Thank you, Mr. Sarkis. And on to Kara Fornstrom.
Thanks, Chris. Hello, everyone. Thanks for having me today. I wanted to talk about our work at the School of Energy Resources at the University of Wyoming on beneficial coal ash reuse. Next slide, please. Before I get to our specific work, I wanted to give you just a little bit of background about the School of Energy Resources. We were created in 2006, and our mission is energy-driven economic development for Wyoming. And so that means that we focus on those energy resources that provide revenue opportunities for the state of Wyoming. Today, that remains coal, oil, natural gas. As many of you know, we're the largest producer of coal in the country, producing 40% of the coal, and we're also a large oil and natural gas provider. However, we're working on emerging technologies as well, and I'll talk about those in a minute. Next slide, please. We have three main pillars at the School of Energy Resources. We do have an academic program, an outreach program, and then our primary focus is on research. And we're applied researchers developing technologies for commercialization, again, focused on economic development opportunities for Wyoming. Next slide, please. The School of Energy Resources is organized around centers of excellence, and you'll see the main 5 research centers there on the left with affiliated centers across campus in other areas. We have our Center for Economic Geology Research, which works on a lot of our permanent storage CCUS projects. Currently we have 4 DOE grants on the Carbon Safe project program going in Wyoming. We have one of the only phase 4 carbon safe projects near Dry Fork in Gillette. And so we do a lot of work on that within the KEGR unit. The Center for Carbon Capture and Conversion, I call them the 4 Cs. That's the center that I'll be focused on today in terms of their research. We have the 3D Visualization Center and the Hydrogen Energy Research Center. Also, we have a nuclear center that is fairly new at the School of Energy Resources, obviously working off the success of the Terra Power project that has indicated it will be located in Kemmerer, Wyoming. And you'll see the other centers there on the right. I lead the Center for Energy Regulation and Policy Analysis. And so we work across all the centers at SCR and across the university to help identify policy and regulatory issues related to Wyoming's energy economic development. Next slide, please. Just a little more about SERPA, the center that I direct. We have 3 main functions. Our primary function is research. We also do policy support of the governor's office, the Wyoming Energy Authority, and the legislature, other state agencies. For that role, we assist on general energy policy issues, regulatory issues. We also help those offices respond to proposed federal rules by providing briefing papers so that they have technical information they need to properly respond to those proposed rules. And then we do stakeholder engagement. So we're engaged with industry groups around Wyoming, such as the Wyoming Mining Association, the Petroleum Association of Wyoming, the Business Alliance, the Taxpayers Association, and others. And I'd like to say that our work, both in policy support and stakeholder engagement, is our ear to the ground kind of work that keeps informing our research efforts to ensure that we are producing meaningful, impactful, high quality work that influences the policy and regulatory conversations that are going on in Wyoming. Next slide, please. So I mentioned the 4C Center, and one of the things that they do there is the Carbon Engineering Program. It was started in 2016, funded by the Wyoming legislature to explore non-thermal uses of coal. As I mentioned, we are the largest producer of coal in the country, and we wanted to pursue some other avenues to see what we could do as a state to incentivize non-thermal uses of coal, given the declines that we're seeing in our coal industry that have hit our economy particularly hard. The Carbon Engineering Program has 12 areas of research, 2 upstream processes. So that includes both solvent extraction and pyrolysis, and 10 downstream product focus groups. You'll see that chart there on the right, and I don't know if it's big enough for you to see those numbers, but the percentages that you see there are based on the weight of the coal, those different uses from coal. The black circles indicate that that's something that you can do with pyrolysis only. The yellow is pyrolysis and solvent extraction, and the red is solvent extraction only. And the program that I'm going to talk about today that deals with rare earths, extracting rare earths from coal, is a solvent only exercise, as you can see there at the top of that chart. For those of you that are non-technical like I am, I'll give you a quick definition of pyrolysis and solvent extraction. Pyrolysis is really just the heating of organic material in the absence of oxygen. And what's significant about that is it's not combustion. And because of that, there are no CO2 emissions. And so we're actually able to produce products that have a lower carbon footprint than many of their conventional competitors. Solvent extraction, the goal there is to use a liquid, which is the solvent, to dissolve a target molecule or a group of compounds and to basically wash them out of that solid material. And that's the process that I'm going to focus on when we talk about our research related to rare earths from coal. You'll see there on that last bullet point on the left, the high volume coal products that we're working on. Those are pyrolysis efforts on the asphalt binder, building materials, and soil amendments. All of those are proceeding in a very good way. We're looking towards commercialization of many of those. Next slide, please. One coal product that I wanted to just highlight briefly before I talked about our rare earths research is our coal bricks, as we call them. We have constructed two buildings that you can see there on this slide. One is built out of the coal-made bricks, and one is made out of conventional bricks. Testing is ongoing about how those different metrics around how those buildings are doing on holding temperature, for example, what kind of leakage you might get, etc. The coal-based products are faring very well, actually exceeding, I think, on most metrics, if not all, related to conventional building bricks. And also the carbon footprint of those is significantly lower. Our asphalt project, which I don't have a slide on, is similarly moving towards, we hope, a pilot project where we will pave 1 mile of a Wyoming highway this summer with coal-based asphalt as compared to traditional asphalt. And that too has a much lower carbon footprint than traditional asphalt. Next slide, please. Turning specifically to our rare earth extraction research from coal ash, you'll see here the rare earth elements on the screen. I think most of you are very aware of why this is important to be producing from a domestic source. You'll see there the light rare earths are in kind of a lighter orange, where the darker orange is the heavy rare earth minerals. Next slide, please. So the goals of the rare earth extraction research project at School of Energy Resources is to extract those and separate the rare earths from coal products, and coal waste, the fly ash. We're using environmentally safe acids, which is pretty much how solvent extraction works. That's the whole point of that, is that it's a much more environmentally friendly way to do that. And again, our ultimate goal is to create economic value in Wyoming. Next slide, please. Our research is ongoing, and we're at a stage that we can't talk a lot about what we're finding. A lot of the work that we're doing is proprietary, and so therefore must remain confidential. However, I can share this slide with you. You'll see there on the bottom the different types of rare earth minerals that we have been able to identify in coal ash from these different coal units in Wyoming, and you'll see those listed there on the right. Those are different colors. And so the four that I just wanted to highlight are the ones that are of the highest value. Cerium is the CE, that's the largest one, and you'll see that at Dry Fork. I mentioned that plant earlier. It's one of the last coal plants that has been built in the United States, highly efficient. That's also where our integrated test center is located, where we're diverting flue gas for specific CO2 research. You'll see lanthanite there, and neodymium, I shouldn't even try to pronounce these, neodymium and yttrium. Those are the four that we see the highest percentages of existence within the fly ash that we're testing in Wyoming. As I said, that work continues, and we'll be excited to present that at a later webinar perhaps, or share those findings with you once we're able to conclude that we are finding promising results. We're really excited about the potential to extract rare earths from coal ash in Wyoming. think that completes my slides. Again, like the other panelists, happy to answer any questions when we're finished. Thank you.
Excellent, thank you. And we are just a few minutes ahead of schedule, so we've got plenty of time for some questions. And we have received a few in the Q&A box. This is probably a question for Mr. Adams, but anybody else, of course, could chime in. This is from John Klein. How many ash harvesting operations are ongoing today? And do you have an estimate of how many have been or are planned?
Well, there's currently 9 facilities that are harvesting right now. The number of planned projects is a little bit fuzzy because people don't want to talk about these things publicly and get themselves committed to anything. But I know one consultant alone is handling 9 proposals. So there are a lot of people looking at it. How many of them will dip their toe into the water and actually go forward is not clear.
And I'll follow up on that myself. What are the substitutes for and I know that you're sort of focused on the concrete and cement industries. What are the options for substitutes for the coal combustion residue?
Well, fly ash and bottom ash together, they're both treated the same now in the ASTM specification for fly ash and coal ash used in concrete. We produce and are selling annually more than double all the other options combined. Slag cement is a very, very good product. We have about 4 to 5 million tons of that sold in the U.S. currently. Natural pozzolans are gaining market share, particularly west of the Mississippi, and they're going to be hitting about 1 million tons, I believe, this year. But the other things like silica fume, ground glass, things like that are coming relatively small amounts. So even when we're looking at a lot of retirements of coal plants, and of course the harvesting is helping to increase supply, we're more than double all the other options. And then we start looking at the options. A lot of the slag cement, whether it be granules or finished product, comes in on both coasts. So the people in the middle of the country don't necessarily benefit from that very much unless you're in the Chicago area where there's a couple of steel mills that produce that particular quality of material. So it's very regional. What we're seeing, interestingly enough, are a lot of blends of these materials to service various markets, and they're working very, very well.
Thank you. Then I believe this perhaps pertains to Tom Sarkis' comments, but is it possible for the unburned carbon to be recovered and to create activated carbon? And is that an economical process if it's possible?
So yes, it is possible to separate the unburned carbon from the fly ash. There are a few processes to try to do that. Recognize that when you do that, you're processing the ash in some fashion. You have generally a physical separation type of equipment, and adding that equipment and running large volumes of fly ash and unburned carbon through it in order to effect the separation is always going to add to the cost. So it's questionable on a case-by-case basis as to whether it's economical to do this separation. From what I remember, and Thomas Adams can correct me if I'm wrong, but from what I remember, the efforts to take that unburned carbon and activate it so that it could become like inactivated carbon, and it doesn't really become the same quality as a commercial form of activated carbon. it's generally not as good, it doesn't have the activation level. So while you could do a few things with it, you can't do a lot. So the preferred method to date, when you do, when it is economical to separate unburned carbon from fly ash, has been to run the unburned carbon through the boiler where it was produced in the first place in an attempt to recover some of the usable energy that's left in it.
Thank you. This, I believe, is most connected to Mr. Sarkis' remarks also. What is the nature of the liability risk surrounding the recovery of this material? And how can that risk be, or the liability or the risk be mitigated?
Well, I'm a technologist first and foremost, and I think you have to study these things. You have to take measurements. You have to perform a variety of tests upon these materials, including leaching tests. And I think that's one of the best ways to do that, is to gather the information, share the information as widely as it needs to be shared, and be transparent with that information. In today's world, I don't know that we're ever going to extinguish the potential for liability on any activity 100%, but we just have to do the best that we can. And, I'm also a believer in technology solutions to the extent that, we can imagine and innovate technical solutions to the characteristics that are causing the liability. I think we should.
Thank you.
I would add to that EPA itself has said the use of fly ash in concrete mixtures is no different than using just mixtures without containing fly ash. So they saw no difference, and they endorsed it when they applied their own risk evaluation back in 2014. So I don't know what kind of liability we would have for an activity which EPA itself says is exempt from regulation, and has also said themselves it's a good thing to do.
Thank you. The next question for Ms. Fornstrom: how does the recovery of rare earths from the ash originating from the Powder River Basin compare to standalone mines in the area? And I'm not sure what we've actually got for mines in the area. You might have to assume a large area.
Thanks, Chris. That's a great question. I should have noted in my remarks that KAGR, which is our geology center, also has an active project going on critical minerals, rare earths, that is much more focused on mined coal rather than the fly ash that the 4C Center is doing. I did not get any specifics about where they are in that research. I know that one is actually probably a little bit further ahead than the coal ash work. But those mines would also be located in the Powder River Basin. I think that's where they're focusing their attention as well. So I don't have any specifics about that, but if someone wants to reach out to me directly, I'd be happy to follow up with them and provide them that information.
Great, thank you. And then a related question. Can you give us an idea what volume of combustion residues are processed to recover commercial quantities of rare earths?
I'm not really sure on that one either, Chris. I do know one of the challenges that we have in the 4C Center that we focus on a lot, and this is one of the reasons that some of the building materials asphalt projects are so appealing to us, is we obviously have a large quantity of coal production to try to replace, given the declines in our coal production, although they are up a little bit, but from historic levels due to the decrease in coal-fired generation across the country. we're working on the economics around all of that and trying to get those things commercialized. At this point, it just doesn't equate to the kind of volume that you get when you just mine coal for the purposes of electric generation and send it out in rail cars. I also think the concentration within those, both just the coal itself and then within the coal ash, are difficult to get in large quantities, but that's one of the reasons that we're working on these extraction methodologies to determine how best to do that and get the highest concentrations and quantities out of the coal ash and the coal itself.
Thank you. Another question for you, not directly related, but what kind of the char bricks is what I'm having in mind right now. What kind of metrics are being studied for the performance of that as a building material, if you can tell us?
I can get you the complete list, but a few that I'm aware of, they're looking at just the weight of those, the durability of them. They're also looking at metrics with inside the house, as I said, temperature, how well it holds the temperature in the winter, how easily it cools in the summer, the kind of efficiency around those bricks compared to conventional bricks in terms of leakage or things like that. I think there's a whole laundry list of those metrics, again, that I could follow with you, but they are robustly testing between the two buildings. And again, they're as identical as they can be in terms of design, location. As you saw, they're right next to each other. And so these metrics are a very clear comparison between the types of materials.
And then I'm sorry for perhaps asking this out of order, but what kind of waste or byproducts are produced by the rare earth extraction process, and then is that continue to be useful as in the form of ash or something, or how does that work?
That is a technical question. Outside of my expertise, Tom Sarkis might be able to answer that better than I can. I'm the policy person, remember, Chris, not the technical guy. So
I have to apologize. I was typing an answer to another question in the chat. What's the question you would like me to field?
What kind of waste or byproducts or residue remains after rare earth minerals extraction? And does that remain useful for some purpose?
Yeah, it depends upon the feedstock. If we're talking about like fly ash, it's a semi-glassy type material that is largely inert. And that actually is one of the difficulties of separating rare earth elements from fly ash. It's kind of embedded in this glassy material, and you have to grind it up. If it's glassy, it's very hard. So you have to grind it up in order to try to recover and separate the rare earth elements. But when you're done, you're going to have the the rest of the matrix of the fly ash. Or if you're starting with roof rock or mine rock from the coal mine, you're going to have like a rocky, clayey kind of material. So it's going to be fly ash minus the rare earth elements.
Very good. Thank you. And I'm not sure who to direct this to. Maybe somebody can just jump in. Is there an expectation that there's increasing availability such that the market might become saturated? And is that a prospect that we're facing?
I'd like to answer that. No, we don't believe that is going to happen. We see that there have been changes in the way ready-mix concrete producers who consume about 75% of the cement sold in the U.S. So they're the ones that would be the most logical ones for consuming coal ash for their mixtures. They have been pulling back for a number of years from using the material in residential and lower specification applications to conserve it for the high demand specifications and projects where they have to have ash in the mixtures. So there's a great piece of the marketplace out there that is not getting any fly ash whatsoever or coal ash whatsoever in their concrete mixtures right now because of concerns over availability. So we have a lot of room to increase use just with the things we're doing, and that's before we see the efforts to decarbonize cement and concrete products to lower our CO2 footprint. That's added a whole new dynamic to this situation. And the only way that the cement companies and concrete companies get to their targets is through using more SCMs of all kinds.
I'd like to echo that as well. I mean, we're not seeing signs of saturation generally. We're seeing quite the opposite. I'm getting the occasional report of fly ash being imported into the United States to assist those regions where it's in short supply.
Interesting.
And to add on to Tom's comment, there are imports coming in. Most of the imports coming in are bottom ash. There is some fly ash. However, the costs for importing and logistics are very, very difficult to overcome. And therefore, it's not a very common activity. India and China would love to send us a lot of their oversupply. They're going into landfills and impoundments in those countries.
That's interesting. What is the reason that they have more than they want or can use, while we are potentially looking for, or not looking for, but while we are experiencing some importation?
Well, very simply, they are more committed to coal-fired generation than the U.S. is in both countries. In fact, 2 weeks ago, I heard one consultant that works in the industry globally comment that China alone right now has 317 coal-fired power plants either on the drawing board or under construction, in addition to what they already have.
Right. Okay. And Ms. Fornstrom, this is an audience question directed to you. Any recovery of gold or other precious metals in the process that you're engaged in?
Not that I'm aware of. We do have separate mining activities going on in Wyoming related to gold that are not associated with the university. But to my knowledge, we have not found gold in any of our work to date.
Very good. Thank you.
At ACAA, we get calls on these kinds of things a lot, and not a lot, but every once in a while, we've had people call and ask about gold. And we even had one gentleman who had a technology which he said worked perfectly in his on his bench, and was looking for $30 to $40 million from us for seed money. So there are some people out there trying to do that, and according to them, having to some success, but nothing we can point to.
Thank you. Another question, I suppose this is Mr. Sarkis or Ms. Fornstrom. Can other elements be extracted during the processing? For example, can arsenic be extracted from the ash to render it safer?
So we are starting to look at that in various research programs. And by that, I mean, we're looking at extracting critical minerals other than rare earth elements, possibly things like cobalt, manganese, things like that. Extracting arsenic to render the ash safer, I don't know that we've looked at that yet. keep in mind again with fly ash, you've got a glassy material. So it's going to be hard to extract those things in the first place.
Great, thanks. Another question for Mr. Sarkis. How does the transportation of coal ash product impact the value proposition? Is this a need? Mr. Adams mentioned that it is a big factor in importation, the logistics and transportation. How about domestically?
Well, I mean, you're talking large volumes when you're talking about things like fly ash, cement, and concrete. And, you know, like anything in large quantities, the less you have to transport it, the more economical your use or your process is going to be. So what a lot of people are thinking about, and I have to admit, not everybody, but I would say the majority of folks are looking at ways to process the ash close to where it sits or where it's produced. And then, you know, we're talking about taking out a very small fraction in the form of rare earth elements, typically on the order of 200, 300, 400 parts per million. And so you remove that and you're left with, you know, with what essentially what you started with minus a few hundred parts per million. It can be transported, but the economics are kind of discourage large volume transport over large distances. It's much easier to process it where it is and then transport the precious rare earths that you produce in small quantities.
For concrete applications, the one exception to what reality that Tom just mentioned is California. Caltrans, the Department of Transportation out there, has been requiring supplementary cementitious materials in their concrete for many, many years, recognizing the durability benefits and on and on. So they've been requiring this material for a long time. And since they have no coal-fired power plants to speak of, all their ash has been coming from neighboring states and even as far away as Illinois and Texas. So that market has been willing to absorb those additional transportation costs for a very long time, but they are the exception rather than the rule.
Okay. Well, thank you, Thomas, Tom, and Kara for sharing your expertise and insight.
Welcome.
Please note, the Subcommittee on Clean Coal and Carbon Management will have a quick business meeting and panel on Sunday, the 25th from 1:30 to 2:30 p.m. Eastern Time at the NARUC Winter Policy Summit in Washington, D.C. The panel will be the economics of carbon capture, getting it done. We will be sharing presentations from this webinar via email with attendees, and the recording will be uploaded to NARUC's YouTube channel. Check NARUC's website for information on other upcoming activities, and please reach out to Catherine or Kiera at NARUC with any questions or feedback. And again, thank you all for being here today and sharing with us.
Thanks, everyone.